minus C1 over omega cos omega t. That might be an interesting exercise. We would take this, call this dy dt, and then separate and integrate with the appropriate limits of integration. That might be a nice way to work through this problem as well. But I'm integrating minus C2 over omega sine omega t. And then since I'm integrating, I've got to throw in a constant of integration. I'm doing an indefinite interval plus 4. But I've already used C3. Let's check that result. ETO. Whoa. I integrated. That's E would be times T. When you integrate a constant, you get a constant times T minus C1 over omega minus C2 over omega sine plus C4. That one deserves a blue box as well. So those are my 4 important equations. How many? How many, he said? 4. How many constants do I have to determine? C1, C2, C3, C4. 4 constants, 4 equations. It all works out well. Okay, so those are kind of our 4 important equations. I'll tell you what, I'm going to write them all right here, and then hopefully not erase this panel at all. Z equals C1 over omega sine omega t minus C2 over omega cos omega t plus C3 and Z dot equals C1 cos omega t plus C2 sine. So, algebraically, 4 equations, 4 unknowns. Differential equation-wise, WIS, not Y apostrophe S. In terms of differential equations, how many orders of derivative did we have? 4. Y double dot and Z double dot were our highest order of derivatives. So we had 4 derivatives, that means 4 constants of integration, 4 equations, 4 constants to determine. And how am I going to determine those? I'm going to determine them from 4 initial conditions. Why initial? Because we're talking in terms of time. So what was happening at time 0? What's y of 0? What's z of 0? What's the starting y speed? What's the starting z speed? That will determine C1, C2, C3, and C4. And if we have those, then we've got the actual motion. So now I'm ready to do this for a couple of cases. Now our E and B fields permeate all space. There's nowhere that our particle can get away from them. So it doesn't matter whether the particle moves up, down, in, out, left, right. These are the fields. We're filling all of space with a downward electric field. We're filling all of space with an inward magnetic field. So I've got a particle sitting someplace. Say my particle is sitting on top of the water bottle. That's its starting position. I set up a set of coordinates, and what's its starting y, what's its starting z? Why don't I care about x? We talked about that half an hour ago. And then I'm going to give this guy an initial velocity. I'll hold my finger back and go bing, and it's going to take off with some z velocity. Maybe I'll funk it downward and it'll have some z velocity and some x velocity and some y velocity. We're ignoring the x velocity because we can always add that in later, like we did for the helix problem. So I give it a starting y speed, a starting z speed, starting y position, starting z position. And then what will this particle do once I give it a thump and make it go? I hold it still, and then I either let go or I throw it. If I let go, of course those two are both zero. If I throw it, then one or both of those is non-zero. We get different kinds of motion depending on what we do. So now I want to look at two specific initial condition sets. I want to see what kind of motion it produces. It's kind of nice not being under the constraint of, oh, I've only got 4 more minutes, how fast do I go? I'm just going to finish this, and then if this turns out to be a double lecture, it does. Or a lecture and a half, it is. But if it turns out to be one full video on Blackboard, it'll be very easy to deal with it. So let's do our first example. In which case we will say the particle starts from the origin. All that is saying, well, here's where my particle is going to start. Now my particle should be this marker lid. There's my charged particle. And wherever it's sitting, we'll say, that's the origin, right there. I declare it to be so. Here's the origin. And the x-axis goes that way, and the y-axis goes that way, and the z-axis goes that way. So there's its starting position. And we'll say it's only going to get thumped, thrown in the y direction. So I'm going to give this thing an initial velocity, bing, that way. What's it going to do? That's what we'll figure out. No initial downward or upward velocity, only horizontal velocity. So let's start to plug those initial conditions in. Let's take the z equation. What do I get when I plug 0 in for that? I get 0. For this, I get 1. So z of 0 is minus c2 over omega plus c3, and I said that was 0. So that tells me, for instance, that c3 is c2 over omega. I've got those equations in the blue box written down somewhere, so I'm just going to do that. I'm going to say, oh, okay. C3 is C2 over omega. C3 is C2 over omega. Now I've only got 3 unknowns because I've used one of my initial conditions. Now let's use initial y. Y of 0, that's 0, that's 0, minus C1 over omega, plus C4. So now I know that C4 is C1 over omega. And you have the nice advantage of being able to shut me off whenever you want to do. And then start me up again. This gets too long, just in there. So now I've got new y and z equations. And I only have 2 unknowns, really. Even though I've got 4 equations, I've only got 2 unknowns. How does that work? How do you deal with 4 equations and 2 unknowns? Well, I really don't. I used this one already. I can't really do something else with that. And I've used this one already. So I have to focus on these other 2 equations to be able to determine what else is going on. Let's plug 0 into z dot. C1 plus 0. So C1 is equal to 0. Okay? Let's do that. Let's get rid of all my C1s. C1 is equal to 0. Right? That's what I said. That's right. Well, we've got our C2. Oh, I use this equation. No, I didn't. I used the Z dot equation.